Hi, this is Kaushik Loud, founder of CardioSentinel at Purdue University. Thank you so much for joining us for the presentation of CardioSentinel. Every catastrophic cardiovascular event has a history before it becomes an emergency. The problem is not lack of data, the problem is the failure to connect it over time. Let us take a situation with Dr. Chandrasekhar Pakmode, a very well known neurosurgeon. 3 days before he died, his ECG showed that everything was fine. The problem is fragmented data and lost context. Episodic fragmented care means patient interactions occur as isolated encounters with minimal continuity across visits or institutions. We have static snapshots. Clinical data is captured as single point observations lacking deeper physiological context. We don't have longitudinal tracking, absence of structured follow ups, scheduled diagnostics, and standardized monitoring protocols. Let us take a look at what the patient clinical data looks over time. If we look at this one particular patient, we see that from 2021 till 2025, when he gets the STEMI event, there is a steady deterioration of his health conditions. But if at any point in time, like, he took a checkup on 2023, for example, because of the lack of structured checkups, he might very well fall within the acceptable ranges for that particular patient's age group and demographics, and the doctors might say you're okay. But if you look at the big picture longitudinally, the problem becomes apparent. Regular longitudinal checkup is important. Risk modeling with all the concomitant factors. The patient's diagnostics are not the only factors. Of course, ECG, blood tests, imaging, medications, and clinical notes are critical. But what is also very critical are biological factors such as genetics, family history, FOAD, circadian rhythms, hormonal changes, inflammation burden, behavioral factors such as smoking, alcohol, drugs, diet and nutrition, physical activity, sleep quality affect the person's health more than you can imagine. And in this day and age, with the amount of pollution we have, environmental factor, heat exposure, noise, seasonal changes, urban living, toxic chemicals matter significantly to the patient's physiological progression. Socioeconomic and psychological factors also affect a person's health. And then, of course, you have the physiological dynamics such as the HRV trends, recovery capacity, sleep variability, blood pressure variability, etc. So, in a real world, what does a patient-doctor interaction look like? I have been to a lot of hospitals in Mumbai, at government hospitals mostly, and this is what I've normally seen. For example, at JJ Hospital in Mumbai, we get 1.6 million patients every year. That's around 5,000 patients a day. The 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 queues are complete. The halls are full with queues. I've literally seen patients fighting with each other for their position in the queue, whatever be that. The doctor has maybe 10-20 seconds with the papers that the patient is presenting them. Many of these patients are from economically depressed areas. They lack education. They lack the knowledge to be able to have comprehensive uh, tests and maintain them over time. So within those 10, 20, or maybe a minute or so, the doctor has to look over the different reports, ask them if you have something else. If they have a CD for an angiography, then wait for a little bit longer, get access to a computer in a different room, load that CD to look at it. It's very difficult, and the pressure on the clinician at this point in time is very, very high. So, what is the solution that we are proposing? Right now in India, we are implementing the ABHA, the Ayushman Bharat Health Account, in which we have the demographics of the patient with the health ID, his consent, everything else, visit history, discharge summaries, everything else. And then we have the HMIS, Hospital Management Information Systems, which is not HIMS. And we have the different data collected, laboratory reports, ECG reports, imaging, angiography, physician's notes, prescriptions, discharge summary, billing, administrative data. But the problem we're facing is that this is raw data. So you have snapshots of these events in the form of PDF documents, pictures, DICOM videos, things like that. This is the intelligence has not been extracted from it. So it is in a sense like if a person is sitting at a desk and somebody comes and drops a bucket load of coins. Yes, it is currency, but at the same time, it is not very usable because you have to sort through it. You have to distinguish it into different, according to its features, and then it is available for you to like disperse. Similarly, intelligence is not extracted from these data points. So what are we talking about with CardioSentinel? So we take the ABHA and the HMIS systems and we link the integration, and we have protocol-driven screening for chronic conditions, for atherosclerosis, diabetes, hypertension, metabolic syndromes, cardiovascular risk, etc. That is first step. Second step would be the structured diagnostic inputs with timed follow-ups, which we think is very, very critical to understand the baseline assessment, follow-up reviews, monitoring the different panels for HB1AC, glucose, lipid profile, KFT, LFT, ECG, and then comprehensive review over a period of 1 year, yearly assessments, and as needed. And now comes the question of how do we convert the data to intelligence? Every cardiac investigation begins with physiology, and the physiology begins with ECG. So we have this algorithm called NeuroKit2, in which we are able to identify and preserve the clinical skeleton of every cardiac cycle by identifying the exact boundaries and the polarities of the PQRST waves. Preserving the morphology and anomalies instead of ignoring the baseline redundancy, the system focuses on the coordinates of intent, which preserves the red flags, such as the T wave inversions, ST segment deviations, or widened QRS complex indicating bundle branch blocks, are captured as discrete digital vectors. And the digital output vector, the stored database entry, is no longer a simple table of timings, but a high fidelity feature set which includes the amplitudes and polarities, intervals and widths, and ectopic flags. And thus, the economic and clinical efficiency is achieved. We are maintaining the diagnostic integrity while reducing the data footprint by over 90%. So what happens, like let's take, for example, we have the 12-lead ECG of a patient coming into the OPD. We have the Holter monitors. We have the intensive care unit, the ECG is being done throughout the day. Then we have the PPG signals, ICD device data from pacemakers, etc. Now we are taking the signal, and we're denoising it, and then the NeuroKit or the BioSpy algorithms are identifying. These are industry standard libraries. We are doing the probabilistic peak detection, and we are segmenting them in the noisy or abnormal signals. And then we have comprehensive fiducial mapping. So we are extracting the complete morphological vector for every heartbeat. The polarity is preserved. All the durations are preserved. The amplitude and measurement and interval measurements are preserved completely. And then we are able to reproduce this with 98.4% accuracy, as you will see later on. And we are also able to handle the ectopic beats, such as outlier beats for PACs and PVCs. Nothing is discarded as anomalous. It is stored with the unique morphological footprint. And thus we're able to achieve rhythm characterization, ischemic markers, conduction anomalies, anomalous beat fingerprints, and longitudinal indexing. So now we're able to take the raw signals and construct that to clinical intelligence. And we're able to reduce the storage size by 90%, but we're able to maintain the fidelity for the reconstruction by 98.4%. So how it is done? So in this situation, we take the raw ECG, we have the skeleton storage model, and 15 key points are taken per heartbeat. And so a 5.2 megabyte, 10-second, 12-lead ECG becomes a 50 kilobyte file. That's a huge reduction. And then we are using the cubic spline interpolation for using the data that we have extracted, the physiological landmarks, and reconstructing the ECG with 98.4% correlation. It is completely accurate, enough for diagnostic purposes of a doctor. Every data packet is timestamped and linked to the patient's medication log, which is very critical. So if at point in time the patient is on certain medication and that affects the patient's heart condition, the doctor will be able to know. So the outcome is that we have clinically meaningful compression, longitudinal continuity, contextual interpretation, which is very important, and scalable and interoperable system. So let's take a deep dive into the NeuroKit to understand how exactly it works. Here is an ECG, 500 hertz, lead 2. Let us see the raw ECG, what does it look like and how the data is extracted. Please note the third heartbeat is an ectopic beat, it shows PVC, and this is converted by the NeuroKit. This is something that is not visible to the clinician. This is the algorithm inside it is working, and you see the beats are being mapped 001, 002, 003, etc. And 003, it raises an alert saying it is ectopic. The QRS duration is 94, and it is being identified as something which is 148, and it is being identified as something which is abnormal. But at the same time, you see on the right hand side column, it says med_context_ID, and it says M102 beta bi, which means that because the patient is on beta blockers, this ectopic beat is not exactly out of the realm of possibility. Okay, and then After that, we are reconstructing, waveform comparison, original PVC versus reconstructed skeleton. You can see that is 98.4% the same as the original. We are not losing anything. We're maintaining the fidelity completely. So again, this is an expansion of that view. So if you have the heart wave, the original injection at 1000 megahertz raw, on the left-hand side, we are recreating it completely accurately, 98.4% validity, and the ectopic nature is preserved, the PVC characteristics are preserved, pathological morphology is maintained, and the contextual information, the medicine's been given at this point in time, is available. Well, so this is what we talked about. So how is the ECG captured for the intelligence? The ECG can be captured directly from the ECG machine. Normally, if you have an ECG machine, it's bulky raw data files, which will take several terabytes of data. But in our situation with CardioSentinel, we're using our advanced algorithms, which results in 90% reduction in storage. And then we are able to reconstruct it with 98.4% reconstruction accuracy. And we also have like watchdogs with clinical review and everything else. Now, what about reconstructing it from an image? So let us say there is an image, there is past data, historical data of the patient. If he has ECGs available in paper format, then we can do that also through image acquisition. So the image is scanned, the image processing will remove the grid, the waveform will be digitized, and signal reconstruction will be achieved using different techniques. And then using NeuroSkit and BioSpy, we would do the same processes as we did before and have a 90% compression and 98.4% accuracy in the reconstruction. So the angiogram shows the lesion and the longitudinal intelligence shows the disease. We have, with our partnership with NVDIA, we have access to the MONAI-based intelligence framework, which is artificial intelligence assisted extraction of clinically relevant vascular intelligence from angiographic DICOM sequences. And so coronary vessel segmentation and topology mapping will identify the coronary anatomy, vessel branching, stenosis regions, lesion localization, and lumen geometry. Feature-based vascular representation indexes the clinically actionable features instead of relying on large angiographic video archives. Instead of having like 500 megabytes or 1 gigabyte of data in a CD, we will reduce this significantly, which will enable reduced longitudinal storage burden, structured vascular indexing, and faster clinical review. The longitudinal cardiovascular intelligence thus transforms isolated angiographic procedures into multi-year lesion tracking, disease progression analysis, longitudinal vascular intelligence, and these will become clear in the next 2 or 3 slides as we show what we mean. The original DICOM is preserved, and the original angiographic studies remain preserved and accessible for full cardiologist review and clinical validation. Percentage stenosis 1 minus d stenosis upon d normal times 100. Anyway, so let us take, for example, we have this coronary angiography situation over here, and here we're looking at how exactly the MONAI works. We will have a pre-processing for noise reduction. We will segment the different vessels, and we will detect the stenosis and quantify it, and then the coronary topology is mapped, and then we will have a feature extraction, and thus the output would be the clinical actionable longitudinally indexable data. We will have the vessel map, we will have the lesion, for example, LAD mid lesion 1%, stenosis 72%, length is 12.14 mm. And then we will have a longitudinal comparison tracking lesion progression or regression over a period of time taken from January 23 to August 24. And then we have the structured report and indexing and efficient storage of intelligence. 90% reduction in intelligence storage footprint. Now, what we're showing is exactly how the angiography will be converted using MONAI into data, intelligence data. No more does the patient have to come with a CD, you have to wait and then basically take it to a different room and pop it into a computer. You already have it on your dashboard. So this is one angiography CD. Let us take a look if you're talking about longitudinal intelligence over a period of time to track the lesion progression or regression over time. What does that look like? So this is the same thing, longitudinal story, longitudinal vascular tracking. Structured angiographic intelligence enables multi-year tracking of stenosis progression, lesion evolution, vessel involvement, post-intervention outcomes. Feature-based coronary indexing, intervention and follow-up correlation, structured intelligence, not just imaging. So this is the holy grail, gentlemen. We have from 2021, 22, 23, 24, 25 where the stent had to be placed, and 26 the follow-up. So we are assessing at 2021 what was the percentage stenosis. 30%, 60.6.2 lesion, and it is in the midsection of the left LAD, and then it just goes from mild to more moderate in about a year. 45% stenosis. It progresses to 75% in 2024, which causes the need for a stent intervention. And after the stent, we're seeing that the percentage stenosis is 10%. And then following it up, 2026, it's 15%. Now, this is like, we're seeing a quantitative trend, LAD mid, for the percentage stenosis on the left-hand side bottom corner, the lesion length, and the reference diameters. All this information is available at your fingerprints at the time the patient walks in the door. And this is how we facilitate decision-making and diagnosis for the doctors and for the patients. So in the future, we will have implementation across multiple departments, cardiology, radiology, where we have X-ray, CT, MRI. FYI, Mona can work also with MRI. So ultrasound and things like that, orthopedics, nephrology, endocrinology, pulmonology, gynecology, pediatrics, ENT, general medicine. We will be able to integrate different elements of the artificial intelligence-based feature extraction from these different raw data and integrate that into the longitudinal structure that we've been talking about. So what does this scenario look like for a doctor? Why should you guys be excited? This is what it looks like. So the patient walks in, his name is, let's say, Jai Jagannath, and we have his health ID, his date of birth, and his demographics. So on the left hand side you see the list of patients, and you have the patient in the center, and you see this wheel with the ECG, the electrical activity, the angiography, the lab results, medications, lifestyle behavior, all this information available at your fingertips. So on the right hand side you see the dashboard, how to use it, and let us say click any section to explore. So let us say that we click the lab results. So when I click the lab results, I can see in an expanded view what exactly are the lab tests being done for this patient. We see, for example, the HB1AC, it was progressing 7.4 to 8.2, but then at 8.4, April 2023, he was prescribed metformin, vildagliptin, and glimepiride, and as a consequence of that, his HB1AC, his blood sugar started getting flat, and with lifestyle changes, it started reducing, which is a great thing. But at the same time, because this is a hypothetical situation, let's take a look at his lipid profile. That is going on without any significant intervention. So we see the LDL and the triglyceride levels increasing, and this is a matter of concern. And we look at the kidney function. We see the ACE inhibitors in October 2024, and you can see the markers over there, creating a good change in his kidney function tests. But unfortunately, we do not have that kind of intervention for liver function, and consequently, it is still going in a progressive way. And similarly for BNP, it is progressing in a not so healthy way. But there is no much acute injury, so the troponin levels remain steady. So this is the holistic view of the patient's metabolic markers, his blood test results. Now let us say that you want to look at his ECG. So 21, 22, 23, 24, 25, 26. We take a look at it and how we see how exactly the ECG is progressing. We're talking about the sinus rhythms in 2021, occasional PACs, non-specific T-wave flattening in the inferior leads. In 2022, we see the increased PACs, T-wave flattening in second, third, and AVF vectors, and borderline LVH voltage. And 2023, we're seeing occasional PVCs, T-wave inversions, mild ST depression. It is getting worse in 2024 with frequent PVCs, ST depression, T-wave inversion, and in 2025, we're seeing frequent PVCs, ST depression, deep T-wave inversion in second, third, and fourth AVF. And lastly, in 2026, frequent PVCs, ST depression, and deep T-wave inversion. So this is moderately abnormal. This is the progression of a patient whose condition is steadily deteriorating and is a cause for concern. Need to change lifestyle, need to change medication, need to basically intervene in a proactive manner to prevent the situation from getting worse. Or potentially this patient could be a candidate for a serious catastrophic event. So how would we, one of the questions that I'm asked often is that has it been implemented somewhere else in the United States or Europe? No, this is a world first system. So why are we confident it's going to work? The reason we're confident is because I have personally worked with Fortune 500 companies and with smaller companies in taking multiple Class 3 life-critical medical devices through FDA quality certification processes. to be able to make it ready for sale and use by the public. The reason that American medical devices and medicines are so efficacious is because our FDA is very, very diligent in terms of like ensuring that we are meeting and exceeding all the quality standards. And we are going to be in compliance with the 21 Code of Federal Regulations 820 for good manufacturing practices, quality system regulations, and the European version of that, which is ISO 13485. We will be using the ISO 4971 risk management for medical devices. And lastly, we will be IEC 60601 compliant for safety of medical electrical equipment. So our device lifecycle quality risk management would be, we would understand the user needs and the intended use. We will use the design inputs and planning, design development, verification and validation, product release, and post-market surveillance. And as a consequence of that, we are able to assure across the entire lifecycle patient safety at every step, regulatory compliance by design, risk control and continuously monitored, quality, reliability, and performance excellent, trust, transparency, and accountability. One of the most common problems we face in medical devices, or like in general also, is that when errors occur, what are the causes of errors? Number one, of course, is the design and manufacturing flaw of the product itself. Number two could be inadequate training of the people who are using the product, unclear instructions, insufficient training, difficult to learn and remember. And lastly would be the real world stress. You're working in a high stress environment with like a lot of patients in an ICU and an OT with high acuity settings, and there's fatigue, urgency, and cognitive overload. So we have to take this into account and make a product which is very well usable and meets the human factor expectations of the people who will be using it. So the impacts are huge. We have fatalities, medical device errors, adverse events, and device errors. So good designs actually save lives, and that's why this is a federal law since 2009 called the AAMI HE75. So we will be having a human factors and usability engineering process with complete front-end research, pre-design. We'll be working with the clinicians, with the nurses, the patients, understanding what exactly they want. We will be having contextual inquiry in real environments, in the OT, in the ICU, in the OPD, things like that. We will be going through an iterative prototyping cycle, test, learn, refine, repeat. So we will be creating the prototypes, running it with you and seeing your feedback, room for improvement, and we will be making something which you are comfortable using with. We're not going to give something that is very outlandish or very technical. And we're going to have design and refinement and optimization with you in mind, with clear controls, intuitive labels, meaningful feedback, logical workflow, error prevention, and minimal cognitive load. We will make your life easier. We will not give you something that is something you have to spend time learning and put an effort into using. No. That is not the way we do things. And thus we will have a design refinement outcome, which is safer use, fewer errors, and better clinical outcomes. So now regarding one of the most critical aspects of it, patient privacy and data protection, we will be globally regulatory compliant. United States, as for the HIPAA privacy laws and the HITECH Act, the 21 CFR Part 11, European Union for the GDPR Act, European Medical Devices Regulation MDR 2017/745, and ISO Directive. We will be completely in compliance with the Digital Personal Data Protection Act, DPDP Act 2023, Information Technology Act, SDPI rules, Ayushman Bharat frameworks, NDHL. And our CardioSentinel has a privacy-first architecture. We will have application layer, role-based access, least privilege, clinical proposed limitations, security layers with standard levels of encryption, data layers with tokenization, data minimization, and physical layer, secure cloud, on-premise infrastructure, geographic data residency. We will be using the latest and greatest technology from NVIDIA, the Tensor architecture, the Blackwell system, which basically is hardware configured for confidential computing and preserve patient privacy. We'll come to that in this slide. So how does that exactly work? CardioSentinel is secure AI execution environment. So we have these confidential virtual machines, in which we have the encrypted GPU CPU communication with encrypted bounce buffers. So and the NVIDIA confidential GPU will be Tensor Core architecture is not, the information being processed over here is not visible to any outsider. So for example, let us say that you have the data in the hospital servers, and we want to process that, and we want to interface that to an outside entity, for example, for training the weights of an artificial intelligence system. In that situation, if we are using the NVIDIA Tensor Blackwell architecture, whatever data that you have in your hospital servers, it is completely opaque to us. We cannot see it. We cannot touch it. We cannot see it. We don't know anything about it. The data will be used by the NVIDIA system to be able to train the weights. And our interest is the weights for the artificial intelligence system, which will then be used for making predictions. Nobody gets access to your data. It stays with you physically. Nobody sees it. Nobody touches it. Complete confidential computing. This is guaranteed by NVIDIA, and you're welcome to look up these specs on the NVIDIA website. So, and to the next step, of course, the natural question is like, what is the cost savings that we're proposing? So let us take for example, JJ Hospital. This hospital has 1.6 million patients a year, and then we have like 5,000 patients a day. So let us assume that for a standard clinical of 500 Hz 12 lead ECG, we have patients per year. We have the numbers over there. Annual raw data is like about 1 terabyte. For the ICU monitoring, the same data is for 27.4 terabytes, Holter monitor and ICD, everything else. The total comes to 528 terabyte. So the core minimum cost just for the ECGs is 31.6 crore or $3.8 million. Now you have to understand this is just the ECG. Indian law requires there should be triple redundancy. So if you require a 528 terabyte system, multiply that by 3 times. And we're not talking about low cost normal laptop storage solutions. No. We're talking about medical grade, hospital grade storage solutions, which have to be up and working for several years. They have to have support. They have to meet certain expectations. And we can reduce that by significant amount to 42.3 terabyte or 2.54 crores. So this is just the ECG. On top of it, this is just the ECG without the 3 times multiplication for additional redundancy. And also there's other factors such as the blood test results and everything else. Thankfully, we have the ABHA and the HMIS systems with which we can tie up, or if that is not available, we can also implement it independent of that. And the pilot program will ensure that we are doing it in scale and we're not blowing out of proportion. We are making something very relevant to prove concept, and we want to add value to the doctors and get the feedback from the doctors and show it to the leadership in the government architecture that this is something efficacious for our doctors and for our citizens. So this again is why is the medical ECG storage so expensive? We talked about this, the medical grade infrastructure is mandated by law. 3 times the uncompressed waveforms, massive storage requirements, 3 times redundancy cost, high power cooling, complex backup. So we're talking about storage and costs like JJ Hospital would be several crores of rupees, and we'll be reducing that by 90%. So this is phase 1, where we have the dashboard. We're presenting the clinical findings, the clinical data in a longitudinal manner to the clinicians. Phase 2 of it is the artificial intelligence part of it, the structured clinical intelligence, which will take, this is phase 1 is structured clinical intelligence, 0 to 24 months. We have the multimodal data inputs from ECG, lab data, imaging and diagnostics, medications, lifestyle and vitals, demographics, everything coming into the CardioSentinel engine. And we create the longitudinal structure with the dashboard which is available to the doctor on demand. And we create what we call the unified longitudinal patient profile. And in this, we have the ECG trends, the lab trends, the imaging timeline, and we assess the overall risk of the patient. So this gives you holistic pictures of the patient's situation at any point in time, because the patient is a system on its own. You cannot take a look at a system with an individual part. In your car, you just don't take care of the tires and ignore the rest. You have to take a look at it holistically. If you miss out on one part, the car is not going to function. The human being is a system, and so we need to look at it from a systemic overview. And then, this is the world first, the artificial intelligence predictive modeling. So we take this multimodal longitudinal inputs, the structured longitudinal feature graph, and then we use temporal AI modeling engine with temporal deep learning, graph neural networks, survival analysis models, causal and probabilistic models, uncertainty quantification, and we create the predictive insights and clinical decision support for risk prediction to see how exactly the STEMI or HF or stroke events can happen in the near future, whatever, and the deterioration forecasting, which would detect the physiological decline before the clinical symptoms actually start occurring. And prevention is better than cure, as we all know. And then we'll have a trajectory visualization for patient-specific diseases and the clinical decision support. And this way, we will be able to provide personalized care pathways, risk-adapted follow-up, treatment optimization, and lifestyle interventions. So the predictive physiological deterioration modeling would be a part of this. We will understand the subtle changes over time, which are not clinically apparent. And for example, the ECG morphology over several years, we will see the subtle ST flattening or the QRS widening, which might not be visible from an episodic ECG. We will see the heart rate variability if the progressive autonomic dysregulation is happening, the laboratory markers to see how the inflammation and lipid stresses are increasing, and the image progression to understand how exactly the plaque burden is progressing. And if the lifestyle behavior is changing, activity is down, stress levels are up, weight is increasing, and if the patient is adhering to the medication and things like this. And we will also be including the hidden convergence patterns such as electrical instability, hemodynamic stress, metabolic dysregulation, structural progression, behavioral risk, inflammatory activation, things like that. And thus we will be having the multimodal temporal fusion, longitudinal pattern learning, bias and probabilistic interference, and uncertainty quantification. And thus, as a result of it, we have the predicted physiological deterioration trajectory. So we'll take a look from 2022, 23, 24, 25, and you see the bar at May 2026, and then exactly how the progression is supposed to go. And in the bottom, you have how the risk is calculated. So let us say the ECG morphology, the HRV, the lab markers, the imaging, lifestyle, and the risk points. So we understand exactly how things are progressing, and then we project that maybe at 2028, there is a very high probability of a catastrophic event occurring. This is the predicted physiological deterioration trajectory, which will be the cornerstone of the predictive environment in phase 2. So from the predictive deterioration trajectory, we'll be creating the early intervention model, and thus we will be able to act before the event occurs. So we will have the risk reviewed by a clinician, family and care team. We will have the intervention at a social work level, social work intervention by the medical social workers and things like that. We will have therapeutic optimization for activity levels, cardiac rehabilitation, increased adherence to diet and exercise and things like that. And we will have closer follow-up monitoring with high frequency visits based on risk, remote monitoring and alerts, and rapid follow-up and trends with dynamic care adjustments. And thus, the clinical impact will be measurable and impactable. We will have earlier risk reduction for up to 12 to 18 months. We will reduce the adverse cardiac events from 30 to 50% as we have, our model right now. And we will have a better resource utilization, 20 to 30% improvement with the resources that you have right now. And we will be making the care much more personalized rather than based on statistics. Again, phase 2 will be completely privacy preserved. We will be using the phase 1 input to create the phase 2 engine, but we will be using privacy preserved AI infrastructure built on trust governed by principles, data sovereignty, end-to-end encryption, de-identification, secure AI computing, and human in the loop. We will be adhering to all the laws and standards that we mentioned before: HIPAA, GDPR, DPDP Act, High-Tech Act, ISO 27001, IRB ethics and hospital policies, compliant by design, trusted by default. Lastly, so what is the projection? We will have the multimodal data pipelines for the ECG, imaging, laboratory, physiological data, clinical context, going into creating the longitudinal intelligence for the patient, going into the phase 2, which will take, this will take around 24 months, we presume, and this will have enough data. This is phase 1, and we will have the clinically meaningful AI models and predictive risk intelligence, which will be used to power the phase 2 from 24 months onwards. And we will have AI-powered clinical decision support, population health management, early detection and prevention at scale, interoperable national platform, research innovation, and global collaboration. And the outcome of this is that this is a world-first system. And we are working with some of the top minds in the world from Purdue and from industry leaders. And the outcome is that India will be as a global leader for AI-driven cardiovascular intelligence and care. And also, lastly, what I want to add is that I believe in India rising to the occasion. In 2017, if you remember, Chidambaram had made some derogatory comments about UPI not being feasible or not being enough point of sale machines and things like that, February 2017. And he said, how would a small seller have this capability? 2017 was also the time when major global corporations, I'm going to leave their name out, they made derisive comments about lack of infrastructure development and that India could never progress to the point of developing complex infrastructure required desperately for its development. And today we have bullet trains. So I believe that, as a people, we rise to the occasion and we exceed expectations, like Kapil Dev's team in 1984. And we have the world's largest population, and we have a system which really needs to be overhauled to be made compliant and to address the needs of our people and our doctors and to give them what every human being deserves: good health and respect. So that is a reason that, even though it is easy for me to, work with structured, curated data from MIT and Stanford, I am choosing to come here and work with raw data from Indian hospitals to make something which is in line with the physiology of Indian patients and make it relevant to the Indian population. Like I said, my father was in the Navy, my grandfather was a freedom fighter, and I want to serve this nation as well. So I request your kind indulgence and helping take CardioSentinel forward. And my name is Kaushik Lode. That's my contact information. And that's my son, Thor. He's 100% disabled autistic, but he's a math genius, wins national math championships, and gets featured on newspapers. Thank you for your time. God bless.